Yes, I usually have to carry cups with lids.
Okay.
And then my wife gets very nervous when I sit in her car with a drink. Although very interesting, though, it has not affected my golf game.
Really?
Even putting.
Like, it doesn't act up at all when you're playing?
I sometimes I'll feel it shaking, but it doesn't seem to.
Okay.
Maybe it's just because when I'm putting, this is my low arm on putting, so I'm not really gripping anything. I'm not really holding weight. I think it's kind of, if I just hold my hand like this, it's not too bad, a little bit. But as I start doing more stuff with my hand, then it starts shaking a lot more. So
Okay.
as long as it doesn't affect my golf game, I'm fine. That's not. I don't really care. When I first started playing competitive golf, I cared a lot more. I played on Golf Channel Amateur Tour, and like, oh, I gotta, I don't want to embarrass myself, right? And then I won a couple of tournaments. I'm like, I kind of accomplished that goal. I'm not gonna be putting food on the table with golf, right? I'm pretty good for like a normal person golfer. Like I look good at the country club. But if I go out there and I try to play on the PGA Tour, I would just embarrass myself because these guys will all hit it 120 yards farther than me. But I don't even care. I usually listen to my audiobooks on the course. I put headphones in, and if you miss a putt, you miss a putt. Who cares? All right. What class is this?
CSC200.
200. So you're not 548.
Did look a little bit yet. Hey, we'll start now. Never too early. You might not know what's going on.
I never know what class I'm sitting in front of. Just gonna have to. 548 stuff's fun.
Yeah.
Oh yeah, we're writing an ARM assembler in there in Android.
Okay.
So you don't know what any of that means. Right?
No. I know what Android means.
So we've talked about low-level languages in here, right? Mm-hmm. So ARM is an assembly language.
Okay.
So ARM is the kind of processors that are like in your cell phones, and as opposed to Intel i86 chipset that's in your computers. Mm-hmm. Each of those chips has a low-level language associated with it. So assembly language. We looked at like the Hello World thing. Mm-hmm. Well, we're writing an assembler on Android for the ARM architecture.
Oh.
So you can write little assembly programs. It simulates it. It's not gonna, so it's an ARM simulator for Android. Okay. So doesn't that sound fun?
That's kind of cool.
Mm-hmm. Works where? For ARM. Yeah. That's actually a pretty interesting backstory because the types of chips that are in our cell phones today are what are called reduced instruction set processors, and those almost died as a processor years ago. Apple used to use these chips called PowerPC processors, which were RISC processors, and the thought was that you put less magic tricks on there, but magic tricks do more, and you might get a performance benefit or something like that from it. Well, it turned out not to really be the case in full-size machines. So they kind of failed. Apple switched over to Intel. We talked about that in here, right? Mm-hmm. So really, everybody went away from reduced instruction set architecture for a while. But then once we had these smaller devices that became computers, now all of a sudden the idea of having less stuff on the chip started making some sense. Mm-hmm. So they made a comeback, and that's where ARM became like the go-to kid now. So ARM is actually an architecture, and then you have various processors. Like a Motorola has a Snapdragon processor, which is a really cool name, right? Mm-hmm. They have their Snapdragon processor is implemented in terms of the ARM instruction set, and so is Apple's. Apple's A11 Bionic or A12, whatever their chip is right now, is also based on ARM. So cool stuff.
Yeah. So
Joyce, get in the 548 class.
I don't think I have prerequisites yet, but
well, actually, I mean, it's a legitimate pitch here, actually. So here we'll throw a real pitch out. So we have a master's program in computer science here. We also have a master's in information technology in the department, and this is an unfortunate truth about I think society today. But the bachelor's degree has become the new high school diploma because everybody thinks they have to go to college. So really, when you end up you spend all this money, you spend 4 years of hell, you come out, you have this piece of paper, and now you're just like everybody else, which is kind of unfortunate. So, I usually try to sell people on this idea that, well, the master's will then set you apart. You know, and it's really not that much more work. I mean, you can finish a master's program in 3 semesters. Yeah. And so what I try to get students to do, if you're going to look into a master's, is your undergrad, you're already paying for up to 18 credit hours, right? That's included. But a lot of students don't take 18. They take 12 or 15. Well, if you can manipulate your schedule in such a way that maybe as a second semester junior or during your senior year, you have 1 or 2 semesters where you have 6 credits open, you can take a master's class early.
Really?
And then you're a third of the way through your master's program. By the time you graduate, you only have 1 year left and you're done. Now, that would be the official case. We've had a student in the past, when we first introduced the program, this was not kosher, right? You know, he took a bunch of the classes as an undergrad, and he had 1 class left, and he had a 1 semester afterwards, and he only took 1 class that semester. He had a master's degree when he came out. So, but yeah, so I mean, you know, if you start thinking about it now and start thinking about your schedule from that perspective, you know, as a junior and senior, you can knock out a couple of the 6 credit hour master's in computer science classes, and get a jump start on the master's, and then, you know, 1 year max, let's say you have a master's degree, and the master's courses are offered in the evening, so you can go out and start working. You know, they're designed for working professionals, so they're 6 to 10 p.m. one night a week is those classes, which isn't, you know, it's a long class, but then you can still have a job, you know, and start getting some experience and stuff like that, and then get your master's degree and either switch jobs or move up within that place. So, you know, if you're interested in more information about the master's program, come and talk to me. I can tell you some more. We also have a master's in information technology. So if you're more the IT side of things, that's a program we can probably also figure something out, very similar offering, except the classes in that are only 3 credit hour classes. So they're easier to squeeze in. The master's in CS we have 6 credit hour classes you can take in any order. So that's the scoop. So everybody should get a master's degree so you're not just like everybody else. So the master's degree is the new bachelor's degree. The bachelor's degree is the new high school diploma. The new high school diploma is the new, hey, I'm an adult now, so I don't have to go to school legally. All right, so we were looking at our toolbox last time, right? So we have a bunch of stuff in our toolbox. We have print and input and int, and we know how to do variables. We saw this thing type, and I mentioned that we probably aren't going to need that often. And as well as ID, we're also not going to need that often. Did I give you a homework assignment for today, or did I tell you you'll have a homework assignment over the weekend? Okay. So let's look here. This is us. All right, so we were going through this stuff here, right? Where was I in here? We did types.
Did we get through them?
I don't know. Where did I stop?
I think he was discussing something about loops.
Oh, I started mentioning about loops. So we have these 2 next sections, loops and branching and loops. So we go back to this idea. I'm going to leave our toolbox here at the end, and that might go to a couple of pages. If you remember how humans solve problems, we remember stuff, we ask questions, repetition. So remembering stuff, that's our variables. So we already know how to do that, right? Some variable name equals some value. Good to go. All right. Now, branching, these are our conditionals. Or here we'll say asking questions. So branching is how we accomplish asking questions. And we do this, I think we wrote some of this last time, but we do this, the syntax is if some Boolean expression, and then a colon, and then you kick it down to the next line, and then you have logic in here. Optionally, you can have an else with a colon and have logic inside that. All right, and you actually could also have some things in there called elifs. So these are else ifs. Whatever. All right. So the only part of this that's required is if you want to ask a question, you ask a question using the if statement, and that has to have some logic underneath it, at least one line indented underneath it. And you can just do that. You can just conditionally do one thing, or conditionally do something. You don't have to have an alternative. You could just say, look, if this is true, we're going to do some stuff. Otherwise, we're just going to move on with life. You can also have an other side to that. So if we go back into our code, I was using Adam last time, right?
Yes.
Okay. I have Adam open somewhere here. All right, that is not us, right? This is us. All right, so that's still not us. No, I wrote that. I wrote another program in here for another class. You don't want this one. Yeah, I pretty much will just throw code wherever, any open window I have. I don't tend to really care where I'm putting it. All right, so maybe did I have the like the drinking age thing last time? Did I do something with that?
Yeah.
Okay.
Yeah, no
So we had something like if your age is 15, so we're going to remember something. We're going to remember what our age is, and then we ask the question if. I usually put parentheses around it because a lot of languages require it, but it's not required in Python. Okay, so I usually say, so I'll say if age is less than 21, then we'll print out, what is it, this bud's for you or something like that? Is that what I said?
Yeah, thanks.
This bud's for you. Else, come back later, buddy. Come back, lady, buddy.
So age is less than 21 for you?
What's up?
Age less than 21 is for you?
Oh yeah.
Yes.
Yeah, see, I did that on purpose. Good catch. Yeah, so this is Wisconsin drinking rules. Otherwise, it's like, aren't you too old to drink? Okay. If age is greater than or equal to 21, if you're at least 21 years old, this bud's for you. Else, come back later, buddy. All right. So this exact same code. So we have a variable here, age is equal to 15. And then we pass that. I kind of think about this as like a filter. So you're kind of dropping this in. If you remember the Plinko, if you what's the game show? The Price is Right, or is that Let's Make a Deal? Whichever one that is. Price is Right. They have that Plinko game where you drop the little coin in the top and it bounces around and stuff like that and lands into one of the slots in the bottom. Think about it kind of like that. So we're dropping age in the top of this, and it's bouncing around and seeing if it passes these different gates. So in this case, age is 15. Is 15 greater than or equal to 21? It's not. So it bounces away from that gate, and we fall into this else. So only one of these two can actually happen. They both can't occur. The else is the otherwise to this. So since age is not greater than or equal to 21, we fall into the else, and this is our catch-all. Come back later, buddy. All right, so if we run this right now, go back out to my terminal. Where's my terminal? You can read that?
Yes.
There we go. Where did I store that guy? So then, oh, not that guy. Is he in? Where did I put you? Desktop. All right, so we'll do Python 3 CSC200 pi, and there's the come back later, buddy. Okay, we remembered something. We remember the age. We asked a question related to the age. Pumped out an answer. Come back in here. We'll change this age to 25, changing nothing else in the code. Now the result of our Boolean expression will be different. Run this again. This bud's for you. All right, makes sense? So let's talk about Boolean expressions, because they're an important part of our branching and looping. Okay, so we have something called a Boolean expression. And this is a Boolean expression is any expression that boils down to a single value of true or false. All right. Now, be prepared over the next over the next many courses, because I'll ask this over and over again. I'll ask you, say, oh, remind me, what's a Boolean expression? It's like a Boolean expression is any expression that boils down to a single value of true or false. And eventually it'll be so ingrained, you'll actually start singing almost like a cult-like type chant. Okay? Okay, well, you'll just say true or false. It's something that boils down to true or false. Okay, so our Boolean types we have true and we have false. Those are the two values that can be stored inside of a Boolean. All right. So these are the things that allow us to ask questions. These are also the things that allow us to loop, because it allows us to say if something is true, we want to do something, and a loop says if something is true, we want to do something over and over again. Okay. So let's look at some Boolean expressions here. Examples. So I'm just going to hard code some, here, we're going to create a couple of variables first. I'm going to say A, it's going to capitalize it anyway, so just roll with it. So A is equal to true, B is equal to false, C is equal to true. All right, so I've given myself 3 variables to play with here. Okay, so now, we can do the mathy stuff first. Let's look at Boolean operators. We have the Boolean arithmetic operators. And these are ones that we already are familiar with. So less than, greater than, less than or equal to, greater than or equal to, not equal to, equal to. All right. These last ones you maybe necessarily haven't seen, but these other ones you've seen before, right?
What's the exclamation and equal to again?
Not equal to.
The last one is
Equal. Okay. So this guy is less than, greater than, less than or equal to, greater than or equal to. All right, so those are our arithmetic ones. So we use numbers with those, right? 5 less than 7, that's true. 7 greater than 2, that's true. Okay? Then we have Boolean logical operators. So this is and, or, and we'll say XOR. We also have, let me check something here real quick. I think in Python 3, it's not like that. Okay, so ands says both sides need to be true for this to be true. Or says at least one side needs to be true for this to be true. And we'll look at some examples. XOR says exactly one side needs to be true for this to be true. And not flips a true to a false and a false to a true. Just flips the Boolean. All right, so these are all operators that, go ahead.
What's how would you use XOR?
I'm not going to be able to give you a real great answer for what we can do with it right now. We typically actually use XORs for in architecture where we're doing bitwise XORs to determine if two things map to a single output. In real life, we might say that, we probably use XORs all the time in real life. Let's say it's sunny outside, and now you can do, you can go to the beach or you can go on a bike ride. Well, you can't go to the beach and go on a bike ride if you only have the 1 hour thing. So you're making an exclusive or type decision. So maybe the first question is, if it's sunny outside, I can do something outside. Now, what am I going to do outside? Well, if I go on a bike ride, I'm not going to go on I'm not going to go to the beach, and vice versa. So only one thing actually happens. Now, we're going to look at something called truth tables here. Did you happen to look at this stuff in 150? Truth table stuff or anything like that? Huh? Oh, you haven't done it yet? Cool. Oh, I see. That's fine. In truth tables they sound more difficult than they are. They're stupid. All right, so I'm gonna draw this, and then we're going to just copy it because that'll be easier for the different things. So typically a truth table, we kind of make a little grid looking thing.
I remember we did it on philosophy.
Yeah. You would do it in philosophy with Manoj. Well, I mean, it's not a memorization thing. It's the logic should work out okay. So let me give myself one more. Nailed it. Okay, actually, give myself one more of these since I'm. At this point, I'm just drawing. All right, so we have a little box like this, and then what we do is we oh, it's exciting. Okay, we'll put that guy in there, and I'll put this guy here, and then we'll put this guy here and change it to a false, and we'll put this. Put this guy here and change him to a false. All right, so I'm gonna copy this 3 times. Well, actually, we'll copy this just 2 times. All right, so we'll do the OR truth table first. So the way this works is we're gonna say true or true. Remember, if we go back and look at the ORs, an OR says at least one side needs to be true for this to be true. So one side needs to be true, or both sides need to be true in order for OR to boil down to true. So true or true is true. True or false is true. False or true is true. False or false is false. So the truth table for an OR is only false when both sides are false. Make sense? So that's the truth table for an OR. Truth table for an AND. Remember, if we look back here, AND says both sides need to be true for this to be true. True and true is true. True and false is false. False and true is false. False and false is false. So an AND is only true when both sides are true. An OR is only false when both sides are false. See how that works? All right. And these aren't really memorization things. These are words that we use in daily life. All right. So just think about how you use your normal logic. If you're going to do something and something else, that implies you're doing both. If you're going to do something or something else, that implies you're doing only one of them. All right, so then the XOR truth table, this is an exclusive OR. That's what XOR stands for, exclusive OR. Says exactly one side is true. So true XOR true is false. We have too many trues there. True, some people call it XOR. True XOR false. I usually say XOR, but a lot of people call it XOR. So true XOR false is true. We have exactly one true. False XOR true. It is kind of fun to say, isn't it? Is true. And false XOR false is false. Do you know that's actually where they got the name for Zorro? You've heard of Zorro before, right?
Mm-hmm.
It's not how they found the name.
I was going to say, like, I don't know how it's related to computer science at all, but
Some things like that are.
yeah.
Yeah. Yeah, a lot of times you have things that are very disconnected that, like how many of you know who Vin Diesel is? Famous actor-y guy. Kind of seems like he's, like rough around the edges, right? Vin Diesel's like a huge geek.
Oh, really?
He's like a Dungeons and Dragons like nerd. Yeah. Yeah. Oh, jeez. Just rub my contact out. Oh, well. I got an eyelash caught or anything or something like that. Whatever. Yeah, he's like super nerd. And when you see him in his movies, that doesn't connect, right? It's like, oh, this guy basically sits around his backyard and blows stuff up. That's his hobby. It's like, no, he plays video games and Dungeons and Dragons and, probably paints little medieval figurines. I can't do that the whole. If you've been in my office, I have artwork. My wife drags me to these paint night things where you go there and you, she doesn't drink, but I drink a lot, and then you paint, and you have an artist up there who they have the painting you're supposed to be doing, right? Some beautiful thing. I go off script real quick. So I've drawn like the Android logo. I got a Pac-Man one in there. I got a Teenage Mutant Ninja Turtle one. I have one. Oh, I have a self-portrait of Mr. Gonzalez.
Mr. Gonzalez.
This guy.
Gotcha. I was about to say, like, it's really familiar.
That's Mr. Gonzalez. Yeah. So, but I don't do a lot of because of the shakes. I don't do a lot of close painting stuff. Mm-hmm. All right. So that's our XOR truth table. Make sense? All right. Now, memorizing these truth tables isn't necessarily important in the big scheme of things. When you're doing high-level programming, memorizing a truth table is probably unimportant for these guys because they're pretty simple ones, right? ANDs, ORs, and XOR, which you're not going to use XOR very often. These aren't hard things to remember. Now, having said that, though, a lot of times what you do is you might create a more complex truth table. Okay, so for instance, we can create a, let me just steal this one. We might have a truth table for, maybe we have a formula. So the formula might be A, I'm going to do some shorthand here, and B or C, something like that. That's Java, C, actually for any of those, double ampersand is the AND. All right. So for something like this, you'd have a larger truth table, right? Because you'd have A's, B's, and C's. But what you'd have is you'd have still your output things here where you would say, okay, if we have an A and a B or a C, both of these guys need to be true, and in order for this to be true, and then this guy over here, if he's true, then the whole thing is true. But you have an output from this guy. Something like this, you wouldn't necessarily memorize your truth table, but if you're doing something fairly complex, you might start by creating a truth table for something and decide if there's an easier way to represent this. Because sometimes you have very difficult math stuff, let's say, that can actually be emulated with Boolean logic. And here's let me show you a good example. Kick it down a line here. So for instance, multiplication. Under the hood in your computers, multiplication is a really expensive thing. Okay, the way it works is expensive. All right, because if you do 3 times 4, you're actually adding 3 to itself 4 times. 3 plus 3 plus 3 plus 3. That gives you 3 times 4, correct? Mm-hmm. All right, so that's how it's implemented, let's call it at the high level, underneath the hood in your computers. Well, we have something called, and this is, we have something called a bitwise shift, which kind of sounds intimidating, right? But let's take a number like the number, I'm going to give you the 8-bit version of the number 4. So that's the number 4 in binary, correct? This is the 1's place, the 2's place, it's almost the 4's place. There's the number 4. All right, that's the number 4 in binary. All right, everybody good with that? Mm-hmm. Okay, so this is 4 in binary. Now, if we do a left shift of that, that means everything is going to move to the left by 1. So we're going to have 1, 0, 0, 0, well, 1, 0, 0, and then we're going to have 0, 0, 0, 0 before that, and then we're going to fill in this new little gap that was created at the beginning with the 0. So we've shifted everything over to the left by 1. We've lost a 0 over here on the left-hand side, and we gained a 0 on the right-hand side. Make sense? Mm-hmm. What value is this?
8.
This is 8 in binary. So we can use left shifts to multiply by 2. So we can multiply by powers of 2 by doing left shifts. So if I do left shift 3, well, here, we'll just do that in the second one. So we take our original thing here and we shift it left by 3. So we're going to have 3 new zeros after this. So it's going to be 1, 0, 0, 1, 2, 3. So that's 6, and then 2 more zeros at the beginning. Yep. So this is the 1's place, 2's, 4's, 8's, 16's, 32's. That's a 32 now, right? Mm-hmm. So 4 times, since we did it 3, that's 2 to the 3rd power, which is 8, is 32. So we shifted 3 times, so we actually took the original value, in this case 4, times 2 to the 3rd power, which is equal to 32. 2 to the 3rd power is 8. That gives us the 32. So basically we can do left shifts to multiply by any power of 2. We can do right shifts to divide by any power of 2. Now, since computers are digital, we're pretty often working with powers of 2. And you can actually do some shortcuts, because sometimes what you can do is you take a number that's not a power of 2, you can divide it into 2 separate values that might have 2 powers of 2. Do the shifts on that, then bring them back together to make multiplication or division quicker under certain scenarios. All right, but we look at this and say, oh, I'm just moving bits around. That doesn't feel like multiplication, or that doesn't feel like division. It's almost like a trick, right? It accomplishes multiplication by a power of 2, or it accomplishes division by a power of 2, and it's just because of the pattern of binary numbers. So sometimes what you might have is you might need a certain kind of output. So you might be writing a video game or whatever, and you need a certain thing to become true. You might draw this truth table for it first, and then figure out what the equivalent Boolean logic for that truth table is. And then all of a sudden you can apply Boolean logic to a math problem without actually having to calculate a bunch of math. Sometimes that works out. And then you're not actually doing the mathy thing, you're just doing something that happens to be equivalent. Right? Does that make sense? Mm-hmm. You know, kind of like if you might make a, let's say you're dribbling the basketball and you kick it off your foot and it happens to go in. You weren't trying to make a basket, but you still made a basket, right? So you did something completely different, but had the same result as if you had really shot the basket. All right. So in any case, I'm going to delete this slide just because it doesn't have real stuff in it, but I'll leave this other stuff in here. I won't have you do bitwise stuff. in here. So you can mark this as kind of not unimportant, but not related to this class. All right. But just kind of showing you this idea of tricks under the hood. Because I mean, just like us in real life, we try to take shortcuts, right? If you're walking from point A to point B, we're supposed to walk on the sidewalks or on the roads or whatever. But, sometimes if you can save a lot of time by cutting through somebody's yard, maybe you do. You maybe aren't supposed to, but you do, right? That's kind of a human thing, right? Well, we do the same thing in computer architecture. We say, what can we do to make life easier for us? Okay, so in any case, Boolean expressions is any expression that boils down to a single value of true or false. Okay? Oh, this is my example thing. I gave myself a couple of variables to start with. So we're going to start off with A and B. What's this guy equal to? A is true, B is false. For an and to be true, what has to be true?
Both of them.
Both sides need to be true. So what's this guy? This guy is false. Okay, A or B? True, because only one side needs to be true. A and C.
True.
Both sides are true, so the whole thing is true. B or, C.
True.
One side needs to be true, the whole thing is true. What about B? Is that a Boolean expression? Have I used any of my operators?
You haven't used any operators.
Do I need to use operators to have a Boolean expression? What's a Boolean expression?
You don't need operators.
No, what's a Boolean expression? What's our
Any
little...
expression that boils
I got to
down-
say it kind of in a creepy chanty way.
Any expression that boils down to a simple value of true.
Single value. Any expression that boils down to a single value of true or false. What's the value of B?
False.
Is that a single value of true or false?
Yeah.
It's a Boolean expression.
Okay.
What about just true?
It's a single book, it's a single value expression.
Yeah. I don't need variables to create Boolean expressions. I have a Boolean literal right there. True. Is true a single value of true or false?
Yeah.
Yep, it's true. I didn't require any boiling down. It just was. Right? It's kind of like eating a raw carrot. You don't have to cook it. You don't have to cut it. It's the carrot. So you say, is that a carrot? Yeah, that's a carrot. Right? Single value of true or false, that's one of them. All right? So one thing to keep in mind here is, and this is more kind of a tip. You've heard this before, right? Don't judge a book by its cover. All right? So we've heard that saying before. So it means just because something looks a certain way doesn't mean that it is what you think it is, right? So always consider what an expression boils down to before deciding what kind of value what kind of expression that is, what kind of it is. Because at a glance, you might look at something, especially for us, we're beginning. So we might look at something and at a glance, it might seem like it's one thing. But if you actually go through the logic and see how it boils down to its final value, it actually is something else. That makes sense? So you want to think through what's actually written and consider what will the output be under certain circumstances and decide what kind of animal am I dealing with. All right? So that's kind of a tip because a lot of times you'll look at something and you'll assume, oh, that's a string or that's a number. And it's actually something completely different. It just involved a lot of strings and numbers that it just happened, it came down to something else. Okay? Now, in the book, Did they have you do anything with making change at this point? Like, you know, you go into a store, and they say something is 38 cents, and you give them $1, right? Now they owe you some change.
Yeah.
Right. Okay, so they had you do something like that with mod, doing the mod stuff to divide it out,
Yes.
to give you how many quarters, how many nickels, how many dimes, that kind of stuff.
Import math.
You shouldn't need import math for that. 'Cause
Well,
you're,
not necessarily for that, but it's
yeah, that's in that section.
right.
Yeah, dealing with that. Okay, so everybody's seen that stuff? All right. What's this?
I think so.
All right. So I'm going to actually show you, I want to make sure this is in our toolbox. Yeah, we have our int. All right, I didn't get to loops. So how can I ask this? I can't really ask it until I do loops. In the book, what have you guys gone? You've done through branching, or you've done through loops?
2.
Okay. So you've done through 3 here, the types.
We didn't do 3.
No.
We haven't done
Oh, you've only done through this section.
Yeah.
Okay. So let's do this instead, because this will bring us where we need to be. For your homework, let's do 3, 4, and 5.
Okay, do Monday, right?
Yep, do Monday. And that'll give us a lot of tools to be able to do a lot of things. So we'll do, we talked about branching today. We'll do loops on Monday, and I'll give you an assignment involving loops on Monday. So do, in the book, 3, 4, and 5 for Monday. Shouldn't be too bad, right? Some reading, a lot of interactive stuff, but it'll get us where we need to go. All right, questions, comments, concerns, bribes. Yep. I usually do my midterms. So for this class, it's we meet Monday, Wednesday, Friday. It'll probably be the Friday after spring break. So I typically do mine after spring break. I'll decide whether it's going to be that Wednesday or that Friday. I might do it Wednesday so I can have your grades back to you by Friday, but we'll play that by ear. But it'll be after spring break, and not the Monday. Not the Monday after spring break.